Good morning, everybody. Happy Tuesday? Maybe? I don't know. Let's see here. I finally have stuff to give back to you. I actually forgot to give this back. So the way this works is I have two folders, right? Section 1 is the 8 a.m. Lab, and Section 2 is the 11 o'clock lab, right? So if you're looking through here and you don't see your thing, then just check the other folder, right? So let's see here. We'll start in the back this time. Let's see, Ashley, you're 8 a.m. Is that right? So we'll start that here. Maxine, you 8 a.m. or 8 a.m.? You 11 a.m.? Yep. Okay, so we'll start that one here. So this one goes that way, this one goes that way. Hopefully they won't get mixed up. Okay, so what's happening Thursday? Right? The exam. Tomorrow is exam review. The way reviews work in my class is you come and ask me questions. I've given you plenty of information up to this point, right? But it's time for you to come and ask me questions. There is a topics list, right, up on Canvas. Tomorrow, I'll answer all of your questions about like the exam format, how to do it, blah, 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 right? We'll get into the nitty-gritties of all of that tomorrow in lab. There's no lab experiment tomorrow, right? The time that we have together tomorrow is just time for you to get all your questions answered, get all the heebie-jeebies out, finish up. Is chapter 4 homework due tomorrow? Right? Finish up chapter 4 homework, right? We just have all of that time dedicated to you and getting your questions answered. If there's a little bit of time today, maybe I'll get started on the exam information just to get you guys all stressed out. All right, I think that's all I've got for you as far as administrative things are concerned. What I wanted to do today is kind of just do more examples of chapter 4 things, projectile motion, what you can do with it. And then we are going to introduce you to the beginnings of circular motion. This topic kind of comes from out of left field. It seemingly, different books do this different ways. This author decides it's good to kind of introduce you to circles because we're going to hit it now. We're going to hit it again with chapters 5 and 6. And then when we finally get to chapter 10, we'll do everything for circular motion. So this is a bit of like a preview, a warm-up, get your brain used to the idea of what's going on, and then we move on. It's justified because circular motion is constant accelerated motion. So that's where that comes from. All right, so variations on a theme. This is a musical term, right? When you have a musical melody and then a performer might play around with that melody and do different things with it. And that's what we're going to do with all of what we know about chapter 4. Let's get our toolbox up on the abomination. Where did I put my, there it is. All right. So let's see if we can remember the toolbox. I think it goes like this. Delta Y. So have you memorized these equations yet? No? Do you need to memorize the equations for the exam? No, because what do you get to bring with you on the exam? Yeah, that summary sheet, that cheat sheet. Sometimes you end up memorizing them just because you've seen them so much, right? Okay. But again, memorizing equations isn't going to save you in my class. So there's our toolbox. Okay, so I'm feeling very old today because my shoulder hurts, but I'm also feeling very old because I guess this year is the 20th anniversary of the Pirates of the Caribbean film with Johnny Depp and Keira Knightley and Orlando Bloom and all that kind of stuff. Dang. You guys have seen that, right? Yeah, it's still kind of become a classic, as it were, right? So I got a situation for you I want to talk about. Let's say that Captain Jack Sparrow, right, in his pursuit of the Black Pearl, right, and this was a deleted scene from the film. Hollywood contacted me and wanted to know if this was feasible, and so we had to run some calculations. That's a total lie, but it sets up the story pretty well. Let's see here. Let's say, and I think in the film, didn't he steal the Interceptor? Was that the name of that fast ship or something like that? Okay. So let's say that Captain Jack Sparrow decides to load himself into a cannon. Now, of course, in the film, they did this differently. I think he just swung over on a rope, right? But he wants to get to the Black Pearl. And you can tell it's the Black Pearl because the sails have holes in it because it's a ghost ship, right? And he lines up a cannon and he decides he wants to shoot himself, right, over an obstacle, the Isla de la Muerte, the Isle of the Dead, right? It's got some of these rocky outcroppings around it, and he's going to try to shoot himself over this obstacle, which, from the point of the cannon, is 10 meters taller than the launch position of the cannon. It's also 50 meters away from the launch position horizontally, okay? So the goal here is to launch over this obstacle. The cannon can deflect itself vertically by 20 degrees, and after loading many stunt people into the cannon, we discovered that they can be launched safely at 40 meters per second. So that's the situation. And the question we're asking is this possible? Right? Can Captain Jack Sparrow make it over the top of that obstacle given the constraints, right, that we have with the cannon and its launch speed and all that sort of stuff? So how do we go about answering that question? Like what could we possibly do to figure this out? Well, okay, we could find max height, right? And if the max height is more than 10 meters above the launch position, does that guarantee that we've actually made it over? So I kind of drawn it kind of weirdly here, but there's different possibilities here, right? There's the possibility that Captain Jack makes it, right? So that could happen on the way up to maximum height, right? Okay, I'm going to erase a lot of these lines. That could happen after achieving maximum height, right? And Captain Jack is on the way down as he clears it, right? Or it could happen like exactly as he reaches maximum height, right? So there's like 3 different possibilities for making it, right? Well, what about the possibilities for not making it? He could not make it on the way to maximum height, right? Maximum height hasn't yet happened, okay? He could launch up and come down and not make it, right? After having been through maximum height. So again, we've just basically outlined 5 possibilities right there. And I don't know about you, I don't want to do the problem 5 times. So max height in and of itself isn't the whole story. It could be a step on the way to figuring stuff out, right? But in and of itself, it's not going to tell us. So what else could we do? So we're definitely going to need time, right? I mean, time's almost everywhere in this toolbox, isn't it? The only place we don't run into time is the third equation. But it's so. Oh, step back for a second. What are we doing right now? We'll talk. Okay, thank you. Yes, we're talking. But like in the problem-solving steps, what are we doing? We're visualizing, and what else are we doing? We're strategizing too, aren't we? We kind of have a picture down, but we don't quite know what to do next, so we kind of try to come up with a little bit of a plan, which might inform a little bit more of our visualization, right? I'm trying to show you that the visualization and strategy are a little bit like they're not rigid, right? You can do one, then the other, then come back to the other, right? Just don't dig into the math right away. We really want to get the physics down. So we know we're going to have to find time. How can we find time? Like what do we know so far? What's the 10 meters? Like in our toolbox, does the 10 meters correspond to anything in here? It is the delta y, isn't it? Okay. Or is it? Like, do we know that Captain Jack is at that 10-meter point? All we need to know is like he clears it, right? So delta y isn't 10, right? It's whatever it's going to be, and we hope that by the time he's 50 meters sideways, that he's more than 10, right, above. So if we solve for delta y when he's 50 meters horizontally, we get 12. What do we know? Then we know he makes it, right? Okay, so delta y isn't necessarily 10. It's easy to get trapped into thinking it needs to be, right? But in this problem, we're trying to figure out if he clears or not. So delta y will help us. So the 50 meters, though, is 50 meters any part of this toolbox? It's the delta x, right? And do we know v naught x? We can find it. We didn't do it, right? Mr. Balogh broke his own rules of just get the components right away, right? So this is 40 meters per second, and we know it's at 20 degrees. So the x component, sine or cosine? It's been cosine the whole chapter, hasn't it? Okay, and we're just being nice to you that way. That all goes away next chapter. All right, so this is going to be 40 cosine 20 degrees because it's touching. And then the vertical component will be 40 sine 20 degrees. So we go and we find out what those are. I got 37.6 for the horizontal and 13.7 for the vertical, right? So I'm being a little bit sort of freestyling here with my my lists. I haven't really made a list, but I've written information down on the diagram. For those of you that like lists, let's go ahead and do that. We know that our V naught y is 13.7, and it's positive because it's going up. We know our V naught x is 37.6 to the right. Do we know our acceleration in the y direction? Once he launches out of the cannon, what is it? Excellent. Meters per second squared. We don't know our delta y. We do know our delta x is 50 meters. We don't know our time. Am I missing anything? Vy. I don't know how fast he's going at some final point, right? So given these things, right, we've already kind of figured out our strategy. What do we need to find first? Time, right? So we're going to, as a plan, right, as a strategy, okay, find time, okay, and then once we know that time, what can we go find then? Then find delta y, right, and see if once he's 50 meters sideways, because the time it takes him to go 50 meters sideways is exactly the same time it takes him to go whatever he's doing, right? Okay, and then we'll compare and see what happens. Okay, so how do we find the time? Yeah, we're going to use the only equation we have for x, right? Because we've got a delta x, we have a v naught x. This will help us solve for time. And then, well, let's just do that right now. So the time here is going to be the distance divided by the velocity. Distance is 50 meters. My initial speed's 37.6 meters per second. Look at that. The units even work out. Time. I got 1.33 seconds. Does anybody else have a calculator? Double check my numbers here. Never believe me when numbers are involved. 1.33? Okay. So that's how long, right, it took to go 50 meters sideways. So what tool can we use to find the delta y? If we know the time and we know the initial y velocity. Second one? Yeah. Because it doesn't have final y velocity, right, which we don't know. And it's already solved for us, isn't it? Find delta y by using the second one. Delta y equals v naught yt plus 1/2 ay t squared. I always like to write it down out of my toolbox because chances are I'm going to mess it up right there. So let's see. We're solving for delta y. We don't know what it is. V naught y plus 13.7 times 1.33 minus 4.9. Again, that's half of 9.8 with a negative sign, and then 1.33 squared, right? Putting all that together. Anybody got it? How many of you think he makes it? Nobody? You hope he makes it? Oh, there's definitely been too much rum because his delta y is 9.55 meters. So what does that mean? This is not going to happen. He is 45 centimeters below the top of this rock pinnacle, right? And so this stunt is impossible, and so therefore was cut from the film, and they didn't do it. That's bad news, right? What could they have done maybe to fix it? Yeah, I think it's the angle that's really kind of screwing them up, right? It's just such a shallow angle. There's other things we can know. Let's find out if Captain Jack is on the way up or on the way down when he hits the rock, right? Okay. How could we do that? How could we figure out if he's on the way up or on the way down? Okay, so I'm hearing an idea where kind of like the max height idea, right? Let's find max height, right? Let's find the time to max height. And let's say the time to max height is 2 seconds. What would that tell us? He's on the way up, right? Because it's only 1.33 seconds, right, to get there, okay? That's one way to do it for sure. And if the time were 0.9 seconds, then he had already passed through max height and is on his way down, right? So how would we find the time to max height? What do we know about an object's motion at maximum height? The final velocity, this is when we can go ahead and stick 0 in for the final y velocity, right? So which of our toolbox equations could help us find the time pretty quickly to max height? Yeah, the first one up here, right? Because we know Vy is 0, we know our initial y velocity, we know our acceleration. So use the first one and solve it for the time. Let's see, that's 0 minus V naught y over negative 9.8. Put in more numbers. 13.7 all over negative 9.8. And I got 1.39 seconds. So if it takes 1.33 seconds to hit the rock, but it would take 1.39 seconds to get to maximum height, he's on his way up, right? Okay, this is like adding insult to injury, right? Okay, he's on his way up. Is there another way that we could determine whether or not Captain Jack is on his way up or on his way down? We could solve for the final y velocity at 1.33 seconds. And if we got a positive number, what does that mean? He's on his way up, right? If we had gotten a negative number, it would have meant he's on his way down. And if we had gotten 0, he would have been at max height, right? So this is why I called it variations on a theme, right? Take a melody and kind of play with it a little bit. You've probably heard Twinkle, Twinkle, Little Star done many times in different genres, right? Those are all variations on a theme. This is variations on the theme of physics, right? We had a situation, and there were lots of different ways for us to kind of get there and think about the problem. The toolbox has its limitations, and we should probably be pretty clear about what those limitations are. What's like the number one limitation, this is like the secret, like superheroes always have a weakness kind of thing, right? What's the weakness of this toolbox? The acceleration can't change, right? And it's tripped up a few of you because you want to say that, something lands and it goes to 0, right? The final speed is 0. Well, yeah, but that's a different acceleration, isn't it? It's come into contact with the ground. It's changed its acceleration. When you have situations like, say, launching a rocket, okay, be it a toy rocket or a SpaceX rocket, right? As that rocket thrust is happening from the engines, is the rocket in free fall? No, okay? And in real rockets, the acceleration is constantly changing. In fact, the acceleration is the slowest at launch. Because after launch, the rocket is burning its fuel. That means its mass is getting less and less, which means, and the thrust stays the same. So same thrust, less mass, it's going to change its motion faster. So there's a really complicated issue, right? When it comes to the changing velocity, changing acceleration as things happen. So what I think I want to do before I get to constant circular motion is just some of you, I'm not going to say you've complained because that's too strong of a word. Some of you have pointed out the profound lack of calculus so far in this class. And we do that on purpose here at Fresno City College. We tend to be calculus light and 4A because, let's face it, algebra is the problem in this class, right? We do a ton of algebra. But I do want to show you something, right? Just give you a little window into how the power of calculus can help with figuring out problems like, say, a rocket launching and the changing accelerations and things that can happen. I've said all this, right? And I don't have my notes. There we go. Okay, so I want to show you how to get this toolbox. Right? I want to show you kind of a little bit where it comes from. I won't ask you to do this on the exam, right? This is just a little added extra on top, right? The little cherry on top of your sundae. So the definition of acceleration. How do we define acceleration? What is it? It's a change in velocity over time, right? And in physics, we might talk about that change using little d's, right? And I know a lot of you are looking at that going, Mr. Bell's derivative. Okay, sure. If you have a velocity function, you take its derivative with respect to time, you will get an acceleration function. That's all true. But derivatives are ratios, right? They're just changes in things. And so we can, because it's a ratio, we can rearrange this slightly. Like that. All I did was multiply both sides by dt, right? Because it's, yes, it's derivative, but more of a ratio. Oh, I can just bust that ratio up and go for it, right? And now I have a little tiny bit of change in velocity and acceleration and a little tiny bit of a change in time. So how do I find the total change in velocity? If I have just a little tiny bit, I can add them up, right? Okay, and the mathematical symbol we use for just add up a bunch of little tiny things is a summation symbol. It just happens to be a special summation symbol, doesn't it? It's the integral. What's the integral of dv? I mean, I didn't put limits on here, did I? But there's no plus c's in physics. We always have limits to our things. So this change in velocity is like from an initial velocity to a final velocity. So this is just going to be v minus v naught, isn't it? And then what about this acceleration right here? So if our acceleration is constant, and I'm going to use constant acceleration just to make sure we get this toolbox, right? But if this acceleration is constant, what does that mean about where it can be in the integral? Yeah, it doesn't get affected, right? What's the integral of dt from 0 to time? It's like the easiest integrals in the world, right? It's just t, isn't it? Okay, so I get v minus v naught equals a times t. And what is this? It's the first equation, right? Okay. So where did we get that from? We got it from a definition. The definition of acceleration is a change in velocity in time. And using the power of calculus, we were able to develop a relationship between all of the velocity and acceleration. Okay, so let's do the same idea, but this time start with the definition of velocity. What's the definition of velocity? Change in position over change in time, right? Again, it's ratio. So I can just mess around with it. Like that, okay? And then I can go in here and add them all up. In the case of x, I'm going to go from whatever my initial position is to whatever my final position is. In the case of time, I'm just going to go from 0 to time. And what happens on the left-hand side? What do I get? I get x minus x naught, right? dx is x, the integral of dx is x, and I evaluate it from x to x naught, right? And over here, okay, this is a little bit more problematic because I'm going from 0. Can I pull this velocity out? Is my velocity constant now? No. But I do know my velocity function. Like I know how my velocity changes in time. We just developed that equation. So I can go ahead and stick that in, v naught plus a times t dt. Oh, okay. Oh, yeah, we're getting into real calculus now. Not really. This is still baby calculus. Okay. What's the integral of v naught dt? Oops. Why did I put an integral symbol there? What's the integral of v naught dt? This is v naught t. And then what's the integral of at dt? It's kind of feeling familiar, isn't it? What's x minus x naught? It's delta x. And what did we just get? We got the second equation, right? We can do it for y, same difference, right? Okay. The third equation comes about by combining kind of first and second to eliminate time. I won't show you how to do that, it's just algebra, okay? And our fourth equation for projectile motion, right, is a special case of projectile motion. But this is how, right, we develop the models for the special case of constant acceleration. So let's take the case of a rocket where the acceleration is changing in time, right? As it loses mass going up. How do we compensate for that? Well, you do this. Only in the first step, can I take that acceleration outside of the integral? No, but I would have to go like measure or determine what my acceleration function is. and it's going to depend on time and some other things, right? I could put that in there, and then what would fall out is a new toolbox, a toolbox that is specific, say, to a Falcon 9 rocket, right? For a given set of parameters. And then if you had a different situation with a different changing acceleration, you develop the toolbox for that one. As engineers, likely a lot of your toolboxes will already be solved for you, right? Physicists, mathematicians, and other engineers have gotten together and we've solved a lot of things. And then we put them together in programs like SolidWorks, okay? And you use those tools to model and simulate and do all those kinds of things. But what happens if you need to build something that's never been built before? What happens if you need to design something that's never been designed before, right? You have to go back to these first principles and invent new wheels. You're not reinventing the wheel. You're using the same process to invent wheels, but it's specific to the case and solution that you are trying to find. So again, I don't do this very often. This, like I said, I teach this class knowing that my audience are mostly engineers and scientists that need to be able to apply physics, right? If you were all physics majors, this is what we would do all day long, right? Because physicists are not concerned really with the answer. We're concerned about where they come from, right? So just giving you a little taste, right, of possibly what you're missing if you had taken this class from somewhere else. All right, let's transition. Let's throw the transmission from like 5th gear to 3rd gear. We're not quite going into reverse, okay? But we are. This is kind of a little bit of a rough transition. So, again, I told you that the reason it sits here is because of the fact that circular motion is a case of constant acceleration. Only its toolbox is different. So I have here my tennis ball on the end of a string, right? And if I swing this around in a circle, okay, and I keep the speed the same all the way around the circle, right? Is this object accelerating? Speed staying the same all the way around? What's acceleration? A change in velocity. And is the velocity changing here? Yes. Speed is not. Speed staying the same. But why is the velocity changing? The direction is changing, right? At every point on this circle, the velocity of this object is changing. If I take and I kind of, freeze the motion, right? Let's see if I can get a decent circle here. I love cheating. Okay, so let's take a point, like, let's say right there, okay, where the ball's right there. And let's say it's going around counterclockwise from our point of view here, okay? So at this point, okay, what direction is the ball going? It's been swinging around like this. Am I doing it in the right direction for you guys? Okay. It's swinging around like this, okay? And we're freeze framing right here. What direction is the ball going? Like straight up? It's tangential to where the string is, right? In other words, like if it's swinging up and it comes to this horizontal position and I cut the string, which way is the ball going to go? It's going to go up, right? So wherever it is, if I cut the string, right, it's going to move perpendicular to where the string was, right? Tangent to the circle. So as it goes around, right, so it will have like a velocity that looks like that maybe, right? Okay. And then sometime later, let's say that we're, over here, okay? Again, same length of vector, but different direction, right? So this is why we say that it has constant acceleration. Question is, what direction does that acceleration point? It's towards the center. If we actually added these, if we took the difference between these two vectors, we'd see that it's a vector that points directly towards the center. Every acceleration vector, no matter where this thing is going to be pointed towards the center. And so we give it a special name. We call it centripetal acceleration. That's how you spell centripetal, okay? Centripetal. That is a very old, like Latin root word that means center seeking. Centri, the center of something, right? And should not be confused with the other C word, which is a very bad word in my classroom. You do not use this bad word in my classroom. Do you know what C word I'm talking about? That's a bad word. That's a bad word. And just so you understand and know what the bad word is, I will say it, but realize that there are tender ears in the audience and you shouldn't be hearing these kinds of things. Centrifugal. Have you heard that term before? Okay. It's center, away from the center is what that word means. Okay. You've probably maybe heard of a device called a centrifuge. Often used in biology and chemistry labs to separate out things. You spin vials really fast, right? And it separates things out. Car designers will talk about the centrifugal force on a passenger, okay? The reason that's a bad word in my class is because it's a fictitious idea. It's a fictitious force. Which way is an object accelerating when it's moving in a circle? Towards the center, not away from it. So why does everybody think it's away? Let's take a ride on the physics bus. Are you ready? Okay. I'm driving the bus up here, right? You're all in the bus, right? We're driving the bus. I'm going 50 miles an hour, right? And I want you to react. Okay. You ready? I'm going to turn to the right. React. Ooh, you get thrown which way? Name the object that pulled you to the left. That's not an object. Forces are caused by objects. Getting a little bit ahead of the game, giving you a preview for next unit. Name the object that pulled you to the left. You're struggling. Okay? That's because there wasn't one. In fact, when we turned right in the physics bus, which way did we accelerate? Where's the center of the turn if I'm turning right? It's towards the right. We get into our mind these fictitious forces and these fictitious ideas, these misconceptions I've warned you about already, right? So let me extend this just a little bit to the idea of sitting there at the stoplight, right? And the light turns green and you hit the gas, right? You're gonna start moving this way across the room. Everybody point in the direction of the force on you. If I hit the gas going this way, everybody point on the direction of the force on you. Some of you are pointing this way. Why? Because when you hit the gas, you get pushed into your seat, right? Name the object that's pushing you backwards. Yeah, what in fact is happening? What direction is your change in motion? What direction is your acceleration? Name the objects that's pushing you forwards. The chair, the car, right? Okay? Everything's forwards, and yet many of you could swear up and down that no, the force, you ask anybody, the force is backwards. We feel that, don't we? But what we feel is our mass responding to the force, right? We're getting pushed on the back. Humans are egocentric, and we say, oh, it's all about us, right? And we say it's backwards. So these are what we call in physics fictitious forces, forces that are made up to try to explain what's going on that aren't real. And in the case of circular motion, there is only one acceleration that happens, and it's towards the center of the circle. And as we learn next chapter, the force is going to follow the direction of the acceleration, a la Newton's second law. But this centripetal, this center-seeking acceleration is what is happening. We can find out what it is, like mathematically, by just taking whatever speed this thing is moving at, squaring it, and dividing it by the rate. I won't show you where that came from, okay? But it's going to be something that we're going to use over and over and over again in this class, especially for things moving in circles. The other thing that we can write down, and something that you've kind of seen before, and we can apply a very simple version of maybe this fourth equation to it. Distance equals velocity times time. This velocity is changing its direction, but it's not changing its magnitude. So we can find the time, the amount of time it takes to maybe go around the circle once. How far does something travel when it goes around a circle once? It goes the circumference, doesn't it? So the distance is 2 pi r, the velocity was v, and since distance equals velocity times time, we rearrange, and we find that the amount of time it takes to go around the circle once is equal to 2 pi r over v. So why did I use capital T there? Do you remember the last lab we did, or the first lab we did? We talked about the period of a pendulum, the time it takes it to swing back and forth. Period, the time it takes to complete something, okay? What are we completing? A circle, right? So we tend to throw in a capital T instead of a lowercase t to represent that we've gone around completely once. All right, so what do we do with this? Well, we do quizzes. We do quizzes, we do an example, and then we will talk a little bit about the exam. How do we find out how fast a person is moving if they're on the equator? What are we looking for? What's the question asking? How fast, right? And what is that? I heard it over here. It's velocity, right? We want to know how fast they're going, right? What's one way we could find velocity if we know something about circular motion? Because this is circular motion, isn't it? Like, if we kind of draw the picture. Well, that sucked. Forgot to turn on my automatic. There we go. All right, so this is like the North Pole. We're like looking top down on the Earth, right? And so a person standing on the equator would be standing right here, going around this way, okay? So what do we need to know to find out how fast they're going? Well, distance is equal to velocity times time. We already developed this, didn't we? We found out that period is equal to distance divided by how fast they're going. That just came from the toolbox for circular motion that we've got so far. So my velocity is going to be equal to 2 pi r over the time it takes, right? So we need to know the radius of what? We need to know the radius of the Earth, right? And then we need to know how long it takes to go around once. How long does it take to go around once? 24 hours. Can we use hours? Is hours the standard unit of time? No, we need it in seconds, right? So now we're back to chapter 1. How do we get from hours to seconds? In 1 hour, there's 3,600 seconds, isn't there? 60 times 60? so that we can find out how long that is. That's 86,400 seconds. Seems like so many for a day, doesn't it? Don't find out how many you spend sleeping. It's a depressing answer. Okay. So, and then we need to go look up the radius of the Earth. How do we find the radius of the Earth? Google, right? Okay. Google, maybe ChatGPT. It might hallucinate, right? But it's out there. It's in your book. Okay, there's an appendix at the end of your book that's got all the planetary data in it. Your book says that it's 6.37 times 10 to the 6 meters. Big planet. So now we go in and we find out what the speed is here, right? It's going to be 2 pi times 6.37 times 10 to the 6 all over 86,400 seconds. And that's going to get me meters per second. And I got 463 meters per second for how fast somebody is going. If they're standing on the equator, how fast are they going if they're standing on the North Pole? 0. If you're standing on the North Pole, saying hello to Santa Claus, what are you doing? Takes 24 hours to do it, right? But that's really all you're doing, right? Whereas on the equator, woo, all the way around. Why do we launch rockets close to the equator instead of the North Pole? Because they're already moving sideways if you launch them near the equator. The further you get away from the equator, the less sideways speed you have. And the secret to getting a rocket into orbit is to go sideways. You want to get up, get out of the atmosphere, but mostly you need to go sideways. All right, and that's if you've never been to a live rocket launch, you really should go sometime because they kind of go up a little bit and then they just tip over and start going sideways, right? And you can't really see that on TV. You don't get the scale of like the path of the rocket as it goes. All right, what's the second part? What's their centripetal acceleration? Well, that's just going to be v squared over r, isn't it? We just found the v, 463 squared, and then the r. What do we put in for the r? It's radius of the Earth, isn't it? We're standing on the equator. And I got 0.0337 meters per second squared. A very tiny center pointing acceleration, but for somebody standing on the surface of the Earth, they will have slightly more downwards pull, okay, because of that. I remember that I went in to get tested in college for a learning disability that I didn't know I had. Would have been really nice to have known that before college. But in my junior year of college, I went in, and as part of the testing, they had to give me like all of it was like 18 hours worth of tests spread out over like 2 or 3 weeks. And I would come in and get tested for a couple and they were like IQ tests and functional tests and problem solving and solve puzzles and do all kinds of stuff, trying to figure out how my brain works or dysfunctions. I remember one of the tests was, it was just like innate knowledge, right? And one of the questions that they asked out of hundreds was, why do Eskimos weigh less than people that live at the equator? I don't remember how exactly the question was phrased. It was probably very racially biased, come to think of it, because I did this in the 90s. But anyway, the grad student that was asking the questions was very bored. She had obviously asked these questions over and over and over again. And I just stopped. Like up to that point, she'd ask a question, and I'd either say, I don't know, or I would just answer it, right? We were going at a pretty good clip. And as soon as she said, like, why do Eskimos weigh less than people at the equator, I just smiled. And she wasn't looking at me, right? But I didn't say anything. And she looked up. She's like, what? I was like, do you really want me to answer that question? She's like, what do you mean? I was like, I can really answer that question. And she kind of put her cards down and she leaned back and she's like, okay, go ahead. And I saw her fingers like reach for the panic button a little bit. And I was 5 minutes into the derivation of centripetal acceleration with respect to your latitude, right? The further away you go from the equator up to the North Pole to explain all of this. And she's like, stop right there. What's your major? I said, well, it's physics. She's like, oh, that explains a lot. Anyway, be careful about what you know. That's the end of chapter 4. And we need to talk about the exam, right? And we need to talk about the exam in a way that you may not have had exam instructions like this ever before. And I want to take the next 15 minutes to do this because it's a very important exercise. And I do want to warn you, I'm about to make you feel very uncomfortable. And there's a reason for this. You have to trust me that this is going to work. Because I need to teach you something about your psychology that you need to be aware of going into any exam you ever take, but in particular, physics exams. What do I mean by that? There is a phenomenon in psychology, especially as it relates to education, called stereotype threat. And so we need to define what that means, how to recognize it, and how to overcome it, most importantly. So for the next 5 minutes, I'm actually going to stop the recordings here. So people on YouTube, you lose. Bye-bye.